Hi, I'm going to present you an introductory talk on the interpretation of deep neural networks and focusing on the motivation for medical application. When you do medical image analysis with deep learning, you have a data set that you split in three: the training, the validation, and test subsets. Then you choose the architecture of your neural network, you choose your loss function, and then you train your network on the training dataset. You monitor your loss on the train and validation dataset, for example, to do early stopping in order to avoid overfitting. Then you can report the performance of your network as measured on the test dataset. Now, are we sure we are completely avoiding overfitting? For example, as the train, validation, and test set are three subsets of the same original dataset, if there is a bias in the original dataset, then there will be the same bias in the three subsets. Another example is when you do diagnosis. If the positives and negatives dataset are from different sources, acquisition protocol, scanner, it is possible that you obtain a very good accuracy, but what you learn is actually to discriminate between different sources and not the clinical features of interest. There is a lot of ongoing work on how to understand the decision of neural networks. One of the tools that has been proposed is attribution maps, which tell you which pixels contribute the most in the decision. For example, for a diagnosis problem, pixels in red here claim that this is a patient image, while pixels in blue claim that this is a healthy subject image. In the next two slides, I'll show you on two examples how we use attribution maps to double-check our training and improve our performance for MS diagnosis of brain tumor diagnosis. So we train a CNN to discriminate between healthy subjects and MS patients. Here we computed the attribution maps, and as you can see, this map is difficult to read and rather noisy. So we propose, instead of training the network directly on the images, to first segment the image into the three tissue class, into CSF, gray matter, and white matter, and train our network using as input not the images, but the three probability maps. So we obtain three attribution maps, one for the CSF, one for the gray matter, and one for the white matter. And as you can see, on these attribution maps, we see features that are clinically relevant for MS. For example, here, in red on the CSF maps, we can see that there is atrophy here in the sulci. On the gray matter maps, you can see that MS lesions are important element in the decision of the networks to classify this image as a patient. We did the same for brain tumor. Here, as you can see on the attribution maps of the CSF, we can find three elements that contribute mostly in the decision of the network. The first one is the tumor here that contributes positively in the decision, which is rather reassuring. Here we can see also that the ventricles are contributing positively in the decision. This is because brain tumors are changing the shape of the element around it, and is that the network has learned to see that deformation of the ventricles are a marker of brain tumor. The third element is the contour of the brain. Here, this might be because the preprocessing of the two datasets we use for healthy subject and patients are different. We use a BRATS dataset for brain tumor images that are already skull stripped. We have to do the skull stripping ourselves for the healthy subjects. So the preprocessing tools for this element probably not the same, and the network probably learned to find some signature of these tools on the contour of the brain. In the next presentation, you will see how to debug and understand deep learning model. To do that, we ask Narina Koklikian to present you this talk. Narina is a research scientist at Facebook. Her research is mostly focusing on the understanding of deep neural networks, and she's also the main creator of the Captum library, which is the PyTorch library to do debugging and understanding of deep learning models. Thank you.